All right, welcome everyone. In today's lesson, we're going to introduce the idea of representing a function as a power series. So this is actually an incredibly important idea that we're really going to investigate over the next upcoming lessons. But today, we're going to introduce this idea. So we're going to see how to represent certain functions as a power series. And specifically, the functions that we look at are going to be generated from 1 over 1 minus x by either multiplication by a power of x or some kind of composition of functions. And really, to get started here, we're going to go back. And we're going to review geometric series. This is kind of the whole starting point for our discussion today. And we know we've talked about geometric series before. We're going to talk about them again. So these are incredibly important. First of all, let's remember what they are. They're the sum. So we have a couple different ways of writing out a geometric series. Sigma notation, we can write it as the sum from n equals 0 to infinity of a times r raised to the n. If we write out the first few terms, it looks like a plus a times r plus a times r squared plus a times r cubed and so on. And we know really everything that happens. We know everything there is to know about a geometric series. We know when it converges, when it diverges. So specifically, when the absolute value of r is less than 1, we know that the sum is a divided by 1 minus r. So when we look at this equation here, we have our geometric series really kind of written out in two different representations. Sigma notation and then with the terms just written out. And then this a over 1 minus r, this is actually the sum. And just for the purposes of review, let's write down when our geometric series is convergent, when it's divergent. So we know it's convergent when the absolute value of r is less than 1, and we know it's divergent everywhere else. So when the absolute value of r is greater than or equal to 1. Okay, so that's geometric series, something we've seen before. We know we can actually find the sum of this. Now we've also kind of found a related power series by essentially setting a equal to 1 and viewing r as a variable x. So we've seen this before as well. A power series, the series sigma n equals 0 to infinity of x raised to the n. Again, the first few terms written out, 1 plus x squared plus x cubed, and so on. And you can kind of see where this comes from. If we go back to our geometric series, we're just taking a, setting it equal to 1, r setting it equal to x, and this is what we're getting. So this is our power series written out in both sigma notation and with the first few terms written out. Now, same thing as above, when the absolute value of x is less than 1, then the sum of this series actually exists. And what is it? It's 1 over 1 minus x. All right, so this is going to give us a starting point, this equation down here. So let's take a look at it. So there's kind of two ways to view that equation. So if we view it as the sum of a series, which we were just kind of talking about, so we're viewing this term 1 over 1 minus x, we're viewing it as the sum of the geometric series, where we've taken a, set it equal to 1, r, set it equal to x. So essentially what we're doing here is we have our power series, the sum of x to the n from n equals 0 to infinity, and we're viewing this 1 over 1 minus x really as the sum. It's the sum of that series. Perfectly fine to do that. But now just think of flipping the equation around. Also perfectly fine. But in this context, we're going to view it slightly different. So this term 1 over 1 minus x, we're just going to view that as just a regular old function. Just some function that we're interested in. 1 over 1 minus x. Perfectly good function. We can plug x values in. Perfectly fine. So we're going to view this as this 1 over 1 minus x. We're just going to view it as a function. And we're going to view this power series as another way to represent this function. So we're going to view this as the power series representation. So in the first kind of thought process here, we have a power series, and then we're thinking of this 1 over 1 minus x as just the sum of that power series. If we flip it around, we're kind of thinking of 1 over 1 minus x as just a function, and then the power series here is a different way to represent that function. It's the power series representation for this function. And that's kind of the key idea here. And so it's this power series representation that's really going to form a lot of what we do in this lesson. So we're going to call it the prototype. The series that we fall back on, that we go back to. So it's written out again. Same one we've seen. We're going to say 1 over 1 minus x is equal to this power series, 1 plus x squared plus x cubed, so on. Or in sigma notation, the sum from n equals 0 to infinity of x to the power n. And we know this works when the absolute value of x is less than 1. We've looked at this before. So we've actually seen that the interval of convergence here is the open interval from -1 to +1. Again, the endpoints, it's worth mentioning here that it diverges at the endpoints. So we know that with the interval of convergence, normally we need to check the endpoints, but for this specific series, it actually diverges at both endpoints. So just worth mentioning there. The radius of convergence is just half the width. So the radius here, the width is 2, so half the width is 1. All right, so this is going to be our prototype that we're going to use to find the power series representation for some other types of functions. And when we look at this, again, we're viewing this as our function. So this is going to be our starting point here. And then we'll be able to figure out what the power series is. And the two things we're looking at is we need, in the denominator here, we need a 1 and we need a negative. So we need that 1 and we need this negative. So those are kind of the two important pieces when we look at our functions. We're going to have things that look similar, fractions that look similar, but the two important kind of components of this before we can go to a power series is that we need this 1 here and we need this to be a negative. So it has to be 1 minus x or some kind of variable term here. All right, so let's try an example to see what we mean. All right, so let's look at example 1. We're going to find the power series representation for the function 1 over 1 plus x cubed. Then we'll also find the radius of convergence and the interval of convergence. So let's kind of start with our prototype. It helps just write it down, just to see what we have to work with. So 1 over 1 minus x is equal to, and let's write out the first few terms. 1 plus x squared plus x cubed. And then let's also write it in sigma notation. So the sum from n equals 0 to infinity of x to the power n. All right, so we just want to start with our prototype just to see what we have to work with. And we're going to compare our fraction here, 1 over 1 minus x, with the function that we're trying to figure out, 1 over 1 plus x cubed. So let's write out 1 over 1 plus x cubed. And when we look at this, again, we said there's kind of two important components that we need. So we need the 1, which, check, we have the 1, but we need the negative. And when we look at this, we don't have that negative. So we have to kind of introduce that into our function here. And the way to do that is with a double negative. So we need this negative here in order to kind of match up with what our prototype says. We need 1 over 1 minus x. So let's write this. Instead of addition, let's write it as a double negative. So we're going to write it as 1 minus negative x cubed. And the idea is this is the correct format now. So we're thinking of this x cubed, negative x cubed here as just a variable. So when we look at 1 over 1 minus x, what we're really thinking is 1 over 1 minus some sort of variable term. And what we're going to do is we're going to look at our starting point, our prototype here. This is what we're starting with. And then wherever we see an x up here, we're just going to change it to a negative x cubed. And that's the big idea. So we're just going to replace x by negative x cubed. All right, so let's just start writing out the first few terms here, just to see what this is going to look like. So we start, what do we have? We have a 1. There's no x to replace there. I have an x. Instead, I'm going to write negative x cubed. Then I have an x squared. Instead of this x, I'm going to replace that with a negative x cubed, so it'll be negative x cubed squared. And then negative x cubed cubed, and so on. So essentially, our variable here is this negative x cubed, and I've gone through, and wherever I see an x, I've replaced it with negative x cubed. And so on. We can also do that for the sigma notation. So we're doing the sum from n equals 0 to infinity. Here I see an x. I'm just going to change that to negative x cubed. So it'll be negative x cubed raised to the n. So again, I saw an x here. Change it to negative x cubed. So that's the idea with this variable, is once we have it in this form 1 over 1 minus, this is our variable term that we're kind of considering, and that's what we're essentially plugging into this power series representation. So essentially I'm plugging in negative x cubed into this representation, and we're getting this. So that's really the idea. So step 2 is to get the correct format. So you might have to do a little bit of formatting here. And that's what we did in this step right here. And then step 3 is to just plug in. So it helps to have that prototype, though, written out just to see what you're starting with. All right. Let's clean this up, though. We can clean this up a little bit. So let's just rewrite the first few terms here just to kind of clean it up. So we have 1, and we can write that as minus x cubed. Then when we square everything here, square the negative, it becomes positive. And when we square x cubed, we get x to the 6. So we add the exponents, or we multiply these exponents here. So it'll be x to the 3 squared, so we get x to the 6. And then same idea over here. We'll have a negative 1 times negative 1 times negative 1. So negative 1 cubed is negative. So we're going to end up with a negative. And then we have multiple exponents, so we multiply the exponents. So we're going to end up with essentially 3 copies of x cubed that we're multiplying together, we're going to end up with an x to the 9. And so on. So here's our power series representation written out with the first few terms. But if we were to write out the actual sigma notation, same idea. So we can break this up. So we have a negative x cubed. So it's negative 1. There's a negative 1 in here. So we would end up with negative 1 raised to the power n. And then the x cubed raised to the power n, just multiply the exponents. So we'd end up with x raised to the 3n. So here we have our function 1 over 1 plus x cubed, and then we have sort of 2 different versions of our power series representation. The terms written out, and then sigma notation. All right. So this is a kind of a fun game to play. Given a function, we're given the function 1 over 1 plus x cubed, we're able to show that this is equal to the power series, negative 1 to the power n, x raised to the 3n, when we're doing the sum from n equals 0 to infinity. All right, so we know that with a power series, this doesn't always work, so we actually have to figure out the x values where this power series does work, and that's our interval of convergence. So let's actually think about what our interval of convergence is. All right. So we know that our geometric series converges when the absolute value of r is less than 1. All right. So what was our r value here for our geometric series? Well, we had it before. It was negative x cubed. So the r value here is negative x cubed for this specific power series that we looked at. That was the variable term that we kind of plugged in, was negative x cubed. Let's just take a look at that right here. That's essentially our r value, negative x cubed. And that's what we plugged in to this formula. All right. So we know a geometric series converges when the absolute value of r is less than 1. So for our specific case here, this is what's happening. Our power series converges when the absolute value of negative x cubed is less than 1. And we know this is true kind of work with this a little bit. So we want to use this to help us find the interval of convergence. So the absolute value of negative x cubed is less than 1. The absolute value kind of cancels off the negative. So we're left with the absolute value of x cubed. So these would be equivalent statements. Now when we have absolute value and multiplication, or powers in this case, we can essentially we have 3 copies of x here that we're multiplying together. So instead of having the 3 copies of x inside one absolute value sign, we can think of this as, instead of x times x times x, all inside one absolute value, we could think of this as absolute value x times absolute value x times absolute value x. So 3 copies of absolute value x. That's absolute value x cubed. So if the absolute value of x cubed is less than 1, well then an equivalent statement would be that the cube of absolute value x has to be less than 1. And doing the cube root of both sides here, gives us that the absolute value of x has to be less than 1. So our power series representation, our interval of convergence, we know from a geometric series here that the geometric series converges when the absolute value of our r value is less than 1. And we've seen that for this specific case, the r value was negative x cubed. And so the condition is satisfied. We have convergence if and only if the absolute value of x is less than 1. So we can write down our interval of convergence. So a way to think of that is just the open interval from -1 to 1, where again we're thinking of all the x values that are less than 1 but greater than -1. So here's our interval of convergence. And we know that with a geometric series, it diverges at the endpoints. So that's just kind of an important point to remember here. Normally, if we were just doing this for any old power series, we would have to go through and check the endpoints. But for a geometric series, we know we have divergence at the endpoints. All right, so it's our interval of convergence is the interval from -1 to 1. And then therefore we can figure out what our radius of convergence is. It's just, can think of it as just half the width. So r is equal to 1. The width of this interval is 2, so the radius is 1. All right, so that's kind of the idea for what we're going to be doing in this lesson of given a function. Here we're given a function, 1 over 1 plus x cubed. We're able to find a sort of a power series representation for this function, and then also figure out what the interval of convergence is, what the radius of convergence is for that power series. And it all kind of goes back to our geometric series. All right, so let's try another example. So let's look at the function 1 over x plus 4. We're going to find a power series representation for this function. And the idea is going to be kind of similar. So we want to start with our prototype. So that is 1 over 1 minus x. This is kind of guiding us for what we should do. We want to make this function sort of match up with this function. And then what is the power series representation? Well, it's 1 plus x squared plus x cubed and so on. And then in sigma notation, it's the sum from n equals 0 to infinity of x to the power n. So the idea is we start with our function, 1 over x plus 4, and essentially we want to make it match. We want to reformat this so that it matches up. So notice in this denominator, it's a constant 1 minus an x. So it seems a little silly here, but let's just really make this thing match. Let's just move these terms around. So it's addition. We have 1 over x plus 4. X plus 4 is in the denominator. It seems kind of trivial, but let's really just make this match. Let's reverse this. So it's 1 over 4 plus x. So we're just getting the constant terms first and then the variable terms second. All right, so there's a few things here. The constant term is, we need it to be a 1. Right now it's a 4, so that's no good. So we need to do something with that constant. And then, again, we have this addition sign here. That's no good either. We need that to be a subtraction. So those are the two things that we're looking at, the constant term and the addition sign there. We need to make some adjustments. All right, so let's start with the 4. Let's see how to work with that different constant. And the idea is we want to factor that 4 off and get it out of there so that it just becomes a 1. All right, so how can we do that? Well, that's what we're going to do. We're just going to factor a 4 off. So we're going to write this as 1 over 4 plus, well, we'll think of it as 1 plus x over 4. So when we factor the 4 off of this first term, we're going to have 1 left over. And when we factor a 4 off of this second term, we're going to have x over 4 left over. So a way to kind of think of this, if you're not entirely convinced of this, another way to kind of handle this is to think of 4 plus x as really 4 plus 4x over 4. And then now each of these has a 4 in it, so we can factor out the 4. So we have a 1 from the first term and an x plus 4 left over from the second term. So we get 4 times 1 plus x over 4. So maybe just another way to think of it if you want to really break down the steps here. So instead of x, we can think of that as 4x over 4. So you just make the number match. And then now we do have something to really factor out. All right, so in any case, we end up with this 1 over 4 times 1 plus x over 4. Let's really split this up now. So this 4 is just a constant, so we're really going to split that off up into 2 fractions. So 1 over 4 times 1 over x plus, 1 over 1 plus x over 4. And it's this that we're going to work with. This is going to be really how we're going to do our power series here. But we're not quite there yet. So right now, the constant term is good, but we still have an issue with this negative. So we still need to make that addition sign. It needs to be a negative there. So we do our usual trick of double negative. So we're going to write this as 1 over 1 minus negative x over 4. And so this negative x over 4, this is going to be our variable part. And so now we have the right format for our power series. So let's write out, just in sigma notation this time, let's write it out, what this is going to look like. All right, so, well, what we're going to do, we have our prototype written out. We have it written out both ways. Let's just use the sigma notation here. So we know that when it's 1 over 1 minus x, the power series is x to the power n. So essentially, we're going to replace the x variable that we see here, we're going to replace it with the variable part that we have here. All right, so the step 2 here was to reformat, which took a few steps. Now we're ready to actually make our replacements. So we're going to plug in negative x over 4 for x. So we're going to plug in this variable part wherever we see an x here. So that's going to give us the sum from n equals 0 to infinity of negative x over 4 raised to the n. So essentially, I'm just taking this x here, and this variable part, this negative x over 4, I'm just plugging that in. So I get negative x over 4 raised to the n. All right, so this is good. This is our power series representation. Let's just clean this up a little bit. So let's start by, we have a few different terms here being raised to the power n. Let's split that exponent up. So we could write this as 1 over 4 times the sum from n equals 0 to infinity of negative 1 raised to the power n, x raised to the power n, over 4 raised to the power n. Pretty good. And then this 1 over 4 that's in front, we can actually bring that inside. It's a constant. So essentially bringing this inside the sigma notation here is like distributing over the addition sign. So we can bring this inside. And so we get the sum from n equals 0 to infinity of 1 over 4 times negative 1 to the n, x to the n over 4 to the n. And then we can combine those powers of 4. So we're going to get 4 raised to the n plus 1. So let's write it out. So our power series representation, we can view 1 over x plus 4. We can view this as the power series from n equals 0 to infinity of negative 1 raised to the power n times x raised to the power n over 4 raised to the n plus 1. So again, we have a 4 raised to the n, and then we have another 4 here that we can multiply together, so we just add the exponents. So that's how we're getting n plus 1. All right, so here's our nice power series representation. And again, it all came down to this prototype, 1 over 1 minus x. We had to go through and do a little reformatting until we got to this point here where we had 1 over 1 minus a variable. So we wanted to match 1 over 1 minus x. We got it to the point where it was 1 over 1 minus a variable term here. And then we just plug in. So we took this variable part, the negative x over 4, and plugged it into our power series representation. So I changed this x, instead of x to the n, we ended up with negative x over 4, all raised to the n. And then we simplified from there. All right, so let's see what the interval of convergence would be and the radius of convergence is. So we know that for our interval of convergence, the geometric series converges when the absolute value of r is less than 1. And for this specific example, we found that the r was negative x over 4. So that means we need the absolute value of negative x over 4 to be less than 1. All right, so let's work with that inequality here. So negative x over 4 is less than 1. The absolute value sign is just going to cancel off the negative. 4 is a positive, so we can think of this as the absolute value of x divided by 4 is less than 1. And then multiply both sides by 4. We get the absolute value of x is less than 4. And so another way to write this is the inequality, the double inequality, where x is greater than negative 4 but less than positive 4. And so that tells us what our radius of our interval of convergence is. So our interval of convergence is the open interval from negative 4 to 4. And again, it's worth noting here, for a geometric series, it does not converge at the endpoints. So if this was just any old power series that we saw in the last lesson, we would normally need to go through and check these endpoints because you might have convergence, you might not. We're talking about a specific geometric series here, so we know it diverges at the endpoints. So here's our interval of convergence. The open interval from negative 4 to 4, excluding the endpoints. And then with that, we can find the radius of convergence. So the radius, again, we can think of it as just half the width. So the width of this interval is 8, half of it is 4. Should always be a positive value. You can also see the radius right in here as well. So when you have just the absolute value term all by itself, the absolute value x is less than that number is your radius of convergence as well. I think it's a little easier just to think of it. You have your interval, think of it as just half your width though. So the width of this is 8, half of that is 4. That's our radius of convergence. All right, so again, here was a function. We were able to use that prototype though to find the power series representation, and then we were able to find where that representation works. So our interval of convergence. Let's try one more example. Let's look at the function x squared over x plus 4. We're going to do the same thing. We're going to find the power series representation for this function, and then we'll find the interval of convergence and the radius of convergence. And to get this started, we can kind of reuse what we did in example 2. So there's a key observation here, is that we can rewrite this function, x squared over x plus 4. We can write this as x squared times 1 over x plus 4. And we already have a power series representation for this. This is what we did in example 2. So let's fill that in. Let's just fill in what we have for our power series representation. What did we find? Well, it was the sum from n equals 0 to infinity. We had -1 raised to the n. We had 4 raised to the n plus 1. And then we had x times x raised to the n. So this was the power series representation that we found. 1 over x plus 4 could be rewritten as the sum from n equals 0 to infinity, -1 raised to the n divided by 4 raised to the n plus 1 times x raised to the n. And what we can do is we can essentially take this x squared term here. Because there is no n, there's no n's here, we can just distribute it over addition. We can move it inside the sigma notation. So we can move that inside. So we can move that x squared. It doesn't depend on n, so we can move it inside. Same thing, if we had this x squared and it was inside, then we could factor it out, again, because it doesn't depend on n. So if we're kind of viewing this as a constant term, so we can move constant terms, we can factor them in, or we can distribute them in or factor them out. So we can move it back and forth between, inside the sigma notation or outside the sigma notation, specifically because it does not depend on n. All right, so let's bring that on in. And what we're going to get is the sum from n equals 0 to infinity of -1 over n, or -1 raised to the n over 4 raised to the n plus 1. We can put this anywhere in here. Let's put it right next to the x. Put our x terms next to each other there. So we'll have x squared times x to the n. And we can consolidate those. So when we have the same base term, what we do is we add the exponents. So we're going to end up with the sum from n equals 0 to infinity of -1 raised to the n over 4 raised to the n plus 1 times x raised to the n plus 2. We've just added the exponents. And so there's our power series representation. And as far as finding the interval of convergence and the radius of convergence, all of the action is happening here with this power series. So it really inherits the same interval of convergence and radius of convergence that this power series had. So we're going to have the exact same interval of convergence. Multiplying by x squared, that's not going to change whether this power series converges or diverges. And so that means the radius of convergence is the same as well. So our radius is 4 as well. All right, so that's really the idea here, is we're given functions. In this case, we had the function x squared over x plus 4, and we're able to kind of rewrite that as as a power series. So there's a different representation for this function written as a power series. And so the interval of convergence is all of the x values where this representation makes sense. All right. So we're going to be talking about this idea of starting with a function and kind of rewriting it as a power series over the next bunch of lessons. And where we're going to go from here is writing these functions as a power series actually makes it easy to differentiate, or potentially easier to differentiate and integrate. So we're going to see next how to actually differentiate and integrate these power series. So we'll see that next time. All right, we'll see you then. Bye-bye.